Okay. All right. So we're going to go ahead and get started. First thing about the exams. I have your exams ready to turn back. They are up here. Those of you guys who have been to LA sessions, that will be reflected on your Canvas scores. The score on the test that's written on the test is just what you've performed in the exam. I will say that there is a trend between attendance to LA sessions and how well you did on the exam, like the raw score. Generally, for every session that was attended, you tended to do about 2-ish percentage points better. Your raw grade was about 2-ish percentage points better. Overall, I think you guys did really well. I think there are a few areas where we need to work to improve, namely vectors is an area where I think a few of you guys are struggling. So you guys will see more electric field problems that force you to use vectors. You guys will see more Coulomb's force problems and other vector related stuff in LA sessions if you attend those. So we are going to be working more on vectors in future weeks. So be aware that that is going to be the course trajectory. You don't get out of doing vectors if you didn't do well on the exam. So we are still going to be practicing this. All right. Today we're doing a couple of things. The first thing that we're doing is we're going to be looking at some optics related. We are returning to this concept of optics, and specifically we are going to be looking at lenses. Now, lenses can be dealt with one of two ways. We can do a graphic representation, doing what we call ray diagrams. And ray diagrams are a way for us to understand, if we use a lens, where an image will be located, roughly how big that image will be, and what will that image look like. So ray diagrams will always start off with drawing an optical axis. And this optical axis is just going to be running parallel through our mirror. Just this wide. So this is our optical axis. This is just basically the center line of where everything's going to take place. We are going to draw in our lens, and there are two types of lenses we will look at. First type of lens is a converging lens. Converging lenses have sort of convex sides on each side. And it's called converging lenses because if we imagine what happens, a ray of light, represent that with yellow because yellow is light, why not? What happens with the convex lens is a ray of light will hit it and bend inwards, and it does so because it's hitting this surface. If we look at refraction that occurs, it's going to refract inwards and downwards. Ray of light coming this way hits the lens, will move upwards, and they did kind of a bad job drawing this, but the point is that the light bends in towards each other. It converges. So this is our converging lens. The opposite kind of lens that we might deal with is called a diverging lens. And a diverging lens has two concave sides. And what happens here is a ray of light comes in, hits the lens. Now, if we look at the normal is going downwards, so when it refracts outwards. Hits, refracts outwards. So our light diverges on this side. We have a diverging lens and a converging lens. So if we have parallel light coming in, meaning all of these yellow rays of light are all parallel to each other, we get the light converging on a singular point. And we call this singular point the focal point. I did a bad job drawing this red line. This red line should go through that focal point. We call this the focal point. This is where it's focusing the light. So all of the light focuses in on this singular point. For the diverging lens, however, all of our light kind of scatters off, right? So it's not focusing the light anywhere on this side. But if we trace the light backwards, we trace these yellow lines backwards. These are imaginary lines. These are not actually here. These are virtual lines, just tracing where the lines would have come from if it was a straight line. We see that they join up right here at this point, which we call a focal point as well. So for a diverging lens, we say that the focal point is on the left-hand side. For a converging lens, we say that the focal point is on the right side. Can we kind of visualize this? Is there any questions, thoughts, comments, concerns? All right. So how is this useful? Well, this can be useful for us because we use lenses a lot when we're dealing with imaging, right? Lenses are everywhere. They're in cameras, they're in projectors, they're on our faces and our glasses. And the behavior of a lens can be one of a couple of different things. It could display a real image, meaning that whatever it's displaying can be projected onto some screen somewhere, like a projector does. It could be a virtual image, so that the image can't actually be projected onto a screen, but we can see it through the lens, kind of like our glasses or a magnifying glass. But all of these behaviors depend on a couple of things. It depends on the type of lens we have. Do we have a converging lens? Do we have a diverging lens? And where is our object in relation to a focal point? So here's what we'll do. We'll take our converging lens. This is the first thing that we'll look at. Converging lens has a real focal point on the right-hand side. And if you look at how we describe focal points of lenses, you'll see some positive value for our converging lens. Our diverging lens, do something similar. I'm going to clear this up a little bit. Draw our optical axis, draw our focal point. For a diverging lens, our focal point would be a negative number. Left on the, we imagine a number line with 0 right at the end, it would be on the left-hand side of the number line, the negative number. So these are where the focal points are. We draw two other points. We draw a matching F prime and a matching F prime. These aren't the actual focal points of our lenses if we're displaying something from the left to the right, but these are the same distances. So both the distance between here and here, and both the distance between here and here, those are going to be the same distances. So we have our foci. We want to see how these two lenses will behave. We want to see how they'll behave when we put an object near them. When we place, let's say, green object. We traditionally use arrows for this because arrows will point upwards. If it's straight up and down, or if it's inverted, it becomes obvious. So we're going to place two arrows. One in front of a converging lens, one in front of a diverging lens. You see how these behave. We examine the tip of the arrow. We can imagine a couple of different scenarios. We can say from the tip of the arrow, imagine a photon traveling straight to the right, parallel to the optical axis. Straight to the right, parallel to the optical axis. And what's going to happen? Well, the converging lens, we just did this a second ago. Parallel light, when it hits a converging lens, will go towards the focus. Just like that. The diverging lens will go away. And I said if you trace this line backwards, it will go through the focus. You just got to trace it backwards. Does that make sense? Does this line seem visually understandable? Yes. Any questions? Okay, so this is our first line. Line 1, we go parallel through focus. The second line, what we're going to do is we're going to go through the second focus that we made. The second line, I'll use a different color perhaps. I don't know, orange. Orange is good. We're going to go through the focus. We're going to hit the mirror, and they didn't do such a great job there. We're going to go through the focus, hit the, not mirror, the lens, and we're going to imagine what happens. Well, if it goes through the focus on this side, it's going to hit the mirror, and it's going to travel in a straight line. You might wonder, why is that the case? Well, flip it around. Flip it around, we have a parallel light coming in, hitting it, and it's going to go towards the focus. So it should make sense to us. So second line, through the focus, hits the mirror, and then goes parallel. Do the same thing over here. Did not draw this mirror or this lens big enough, but it's going to hit the lens. What's going to happen here? What do we think?
Then you go parallel.
We think it's going to go parallel. After it hits the mirror, it's going to diverge even more. This is not a useful line in this case. Instead, what we're going to do is not aim for the focal point on the same side, but just like on this side where we aim for the focal point F prime, I know I just erased that prime, we're going to do the same thing over here. We're going to aim for F prime. But once we hit the mirror, we're going to go parallel. Aim for F prime. I didn't even aim for F prime too well. That's why it didn't look right. We're going to aim for F prime. Imagine that dotted line saying that's where we're aiming. We're going to hit the mirror. We're going to go parallel. That looks right to me. And why do we do this? Well, we do this because we imagine the light coming in this way, hitting the lens, refracts outwards, diverges. What we're going to do is we're going to take this line, draw it backwards. That'll make a little bit more sense here in a moment. But that is our second line. We aim for F prime, whether it's on the same side of the mirror or not. We aim for F prime, and then once we hit the lens, we go parallel. So aim for focus, I should put focus prime, F prime. Does that make sense? Can we see this? Yes.
What happens if the first line does go through the one on the concave one?
It's just not going to be super helpful to us. So we imagine it goes down. It's going to hit it. It's just going to diffract further outwards. It's still valid, but it's not really helpful for us in this situation. It goes too far off for us to be able to use that line. So with these two cases, we see that these lines intersect. It's more obvious over here, where the lines intersect right here. And they intersect in a way that will give us an image at that location. Where these lines intersect is where our image is located. So for the case of the object being on the outside of the focal point, it's going to hit the lens. It's going to project upside down. If you guys have ever seen projections from just a single lens, those projections are inverted. So we get inversion in the case where our object is behind the focal point of the lens. But we get a real image. We can physically put up a screen on this side of our lens, and we can project this image onto. You'll see this in lab in a few weeks, just to prove that, yes, you do actually get these images where these intersect. There is a third line we can draw. And we do this typically just to double check our work. And this third line is actually really simple. It's just a straight line. It's a straight line that will hit the lens right at the optical axis. and did not do such a great job here, is these should intersect. On your classwork, there will be a better image. But this line just goes straight through. Again, I'm not doing such a great job because my focal points aren't nearly equal to each other. You get this straight line and you get this, them all intersecting at the same place. With this one, our straight line had something like that. We get all three lines intersecting at this point. And yes, we did have to trace back two of our lines. Our yellow line we trace back, or orange line we trace back. What we end up with is an image on the right-hand side of our mirror, or sorry, I keep saying mirror, I mean lens. Get an image on the left-hand side of our lens, and this image is smaller. And it's also what we call virtual lens because we can't actually put a screen right here to project our image. The only way we see this image is if we look through this end of the mirror, lens, saying mirror. We look through this side of the lens. That is the only way we see this image. We don't see it in real life. It's not really a tangible thing. So when our image is on the left-hand side of the mirror, on the left-hand side of the lens, when our image is on the left-hand side of the lens, we call it a virtual image. It's on the right-hand side, we call it real. So this one is real, and it's inverted. This image is virtual and non-inverted, as it is standing straight up. You will be doing one of these ray tracings in your work today. You'll be doing a different case. You'll be doing what happens if our object is inside the focal. We'll see what happens. This is actually the same. What you do in the classwork today is going to be essentially how magnifying glasses. And all this is great for visualization, but we're here in physics and we're here to do the math. We're here to figure out a couple of things. Things that we might care about in physics is locations. Locations of images. Depending on where the object is, we move the object back further, the image moves back further. Why does this matter to us? Well, let's say we were building this lens to be the lens of a camera. We want to take a picture with this. If we want to take a picture with this, we have to put the film in just the right place. When you focus your camera, what you're doing is you're moving the lens in accordance to whatever is the image is being projected onto. So if it's a digital camera, whatever sensors exist, if it's a film camera, you're physically moving the distance between the lens and the film to get it into focus. Because you want this to be exactly where the image is. So you might care about distances. And there's a relationship between the distance B subscript O, distance of the object, the thing that we're taking a picture of in this case, the focal length, call this F, is the focal length. And distance of the image DI. Again, there are much better diagrams in your classwork that you'll be dealing with today. But these things are related by what we call the thin lens equation. The thin lens equation works under the assumption that this lens is very, very thin. The thin lens equation tells us that the inverses of your object's position and the image position add up to be the focal length, meaning 1 over distance of the object plus 1 over the distance of the image is equal to 1 over the focal length. That is the relationship between the object's distance, the focal length, and the image distance. The other thing we might care about is magnification. Magnification meaning how tall is our image compared to our object. So we say, all right, this is height HO. This is height HI, H subscript I. So our image height and our object height are given by these. And we define magnification by being the height of the image over the height of the object, HI over HO. This is magnification. So if you have 2 times magnification, that means your image is twice as large as your object. This is related to your distances. Right, negative DI over DO. This is derived from the thin lens equation. We'll see that derivation later on, but for right now, just take it as truth.
It's
That
negative, right?
it is a negative. Yeah, it is a negative. I had to double check that. And usually we just represent magnification by capital M. So this is your magnification. This tells you how big is your object. The further away the object is from the mirror, the lens, the larger it's going to be. And this is the basics behind lenses, specifically the basics behind thin lenses. We'll be seeing this throughout the rest of the semester, playing around with these and understanding sort of the behaviors between real and virtual images. Eventually, towards the end of the semester, if we have enough time, we'll look at combining lenses to create effects like what you see in a microscope or a telescope. See how those specifically work when we stack lenses. But for this moment in time, we're just looking at this idea behind the thin lens equation, magnification, and this idea of ray diagram. Again, much better pictures that you'll see on your classwork because not so great at judging images, distances on the board. Are there any questions about this? Any thoughts, comments? Yes.
I noticed this is kind of similar to what we covered last week.
Mhm.
Are you like doing a continuation of last week, or is that just today?
This, what we're doing today was supposed to be what was covered on Thursday. I had to cancel class. So this is from last week. Your homework was extended because I canceled class. But yeah, this was on your homework. Yes. F? F is your focal length. It is the distance from the lens that light will focus. So you have parallel light coming in, bends it into this point. I don't know if any of you guys were a little bit of pyromaniacs in your youth, but have you ever used the magnifying glass to focus sunlight to burn a leaf or something? Burn ants, if, yeah, sure, wasn't gonna go there, but yeah. The focal length is the distance you would need your ant to be from your mirror. It's where the light is being focused in. Are there any other questions? Okay, we feel all right about this? All right. We're covering one more crucial topic today. And this topic is getting into more realistic situations, not completely realistic. We're still going to make assumptions, but we're going to look at charge distributions. So up until this point in time, we have been dealing with charges as though they were singular points with no volume, right? But we're going to start looking at what happens when those charges actually have volume. What happens if instead of a point charge, we are looking at maybe a line of charge. To start out, what I'm going to say is, imagine we have a singular charge, just a singular charge. We have a singular charge, the electric field would be pointing in all directions, right? We saw this last week. I'm just gonna draw those ones. We're gonna look at a point P. And by this location right here. P. The electric field here is pointing straight up, right? Depends on the distance from this charge, the electric field is pointing straight up. We can calculate the strength of that electric field. We can say that that is, I'm going to say E1 is equal to K Q1 over R squared, right? That gives us our electric field. And right here, it's going to be pointed straight up. It's going to be in the Y direction. We add one charge, and this is what our electric field is. Now let's imagine we add two more charges right next to each other. Right there and there. Well, last week we saw when we had three charges that we had them arranged vertically and the vertical component canceled out, right? We were left with only a horizontal component. Same thing happens here and here. The horizontal component is going to cancel out, and both of these are going to cause electric fields going off in that direction. When you add them up, it's going to be just completely upwards, right? Horizontal component is going to cancel out. We say that is E2 and E3. Again, given by those saying KQ, and R is slightly different. We continue this argument and we add charges to infinity. You just add an infinite number of charges, and we can calculate the electric field from each of these charges, right? And for each of these charges, it's going to have a second charge to make a pair that will cancel out our horizontal component. So if we add all of these charges, we should have no horizontal component. We should only have a vertical component of electric field. Do we agree? Yes? No? Maybe? Do we see this? Okay, fantastic. So how do we find the electric field at point P? Well, we find the electric field at point P by saying our electric field net is equal to the summation of all of our individual electric fields, represented EI, right? Just add up our electric fields. But if we have an infinite number of these, then maybe a summation isn't good. We'd be here our entire life. Yes.
Sorry, what is this E base what?
E net or net electric field is equal to the summation of our individual electric fields. So what might be a good idea instead of summing an infinite number of things? What mathematical techniques have we learned to deal with technically infinite? Integrals, absolutely. So instead, we dive into calculus and we say that our net electric field is going to be the integration of each of our individual electric fields. And we say that each individual electric field gives us a little d, a little sliver of electric field, just a little chunk. dE, well, what's causing these electric fields? Say our individual charges, dQ, each charge, each little charge dQ gives us a little bit more electric. Do we agree?
I don't know.
You don't know? Well, if E is equal to KQ over R squared, then if we say we have a little selection of dE that's coming from a little bit of charge, dQ, coming from one of these individual chunks. Yeah? Okay. So what do we do with this now? Well, we start to consider this as a singular object. We consider this a singular object, a singular line of charge with all of these little chunks dQ in it. And if we have a line of charge, with lines of charge, we start talking about linear densities. Now, this is something you should have seen last semester, where our linear density lambda is simply going to be the amount of charge Q per however long our length is. So we say our line of charge has a total charge Q, and it is however many meters long it is, right? And we go from integrate from minus L over 2 to L over 2, get our full length. We're integrating over the entire line. We're doing a line integral. We want just a small charge dq. We're looking at a small change in length dl. Yeah. Q over L is equal to dq over dl. This is just an argument using densities, right? If you have regular mass density, right? We just look at regular mass density that we're familiar with. Mass over volume. If you have the volume, you have the mass. If you quarter the volume, you quarter the mass. You have just a small chunk of mass dm related to a small chunk of volume dv. So we solve this. We say, all right, dq must be equal to lambda times dl, where L is going to be our length along the axis. Since we're looking at changes in the x-axis, right? We're moving horizontally. So we say our changes here are going to be lambda dx. dx is the thing we are integrating over. dx, our position x, is the thing that is changing for each of these charges. So this changes our integral. Negative L over 2 to L over 2. K times lambda dx over r squared. I'm going to erase the bottom half of this board real quick, so be sure to write it down. All this is just an argument in density. An argument that is similar to the same arguments that were made when you were looking for center of mass of objects. So where do we go from here? Well, the next thing we might care about is how is this value R changing with X? And how it's changing with X is dependent on the same triangles we've been drawing all semester. We have a dx, if we have a change in x, we have a change in r that's according to this right triangle, meaning that we're looking at this charge right here, position x down here. Well, r is equal to the square root of how high up we are. I'm just going to put y as a stand-in, y squared plus x squared. This is just a description of how long this hypotenuse length is. Hypotenuse length, we have a distance separation from the line. Point P is a distance y away from the line. We're distance x over, so r is equal to square root y squared over x squared. That changes our variable. L over 2 to L over 2 of k lambda dx over r squared. We know r is the square root of y squared plus x squared, so it's just y squared plus x squared. But we don't have the full electric field, right? We had some cancellation. We had our horizontal components canceling out. So it's not the full electric field. Instead, we just have the sine of whatever angle theta we have. So if that's angle theta, sine of theta. And that sine of theta is there specifically because pairs of charges are canceling out the horizontal components. We're only left with the vertical component given by sine of theta. Sine of theta is opposite over hypotenuse, right? Opposite is going to be, yeah. Opposite is that distance y. This is going somewhere, and don't worry, it's not as bad as it looks. K lambda dx over y squared plus x squared. The opposite is going to be the distance y. We have a y up top. And the hypotenuse, we just said, is square root y squared plus x squared. So now we have only that value x change. Y is a constant. Y is just how far away from the wire are we? Lambda, that's a constant. That's just how much charge per distance our wire has. K, that's a constant. So the only thing in here is changing is x. And our integral is with respect to x. So this is an integral that we can, in fact, solve. We can do a little bit of simplification. And our simplification looks, I'm running out of board space. Didn't write so big, probably. I'm going to erase it right here. Saying our electric field is going to be the integral from L over 2 to L over 2. And then we have K lambda. I'm going to move the y up here over y squared plus x squared to the 3/2 times dx, right? So our square root and our whole thing add up to being 3/2. K lambda and y I'll pull out front. Integral of 1 over 3/2 of y squared plus x squared. This is actually a trig substitution, but the results of this integral give you, I don't want to mess this up, K lambda y K lambda y times x over y squared square root. Square root x squared plus y squared. And then evaluated from minus L over 2 to L over 2. This is the results. Now, all of this is just to argue that this is the result from our charge. And again, you do have to evaluate this over the limits. And a very special case occurs when we have a very, very, very long wire, nearly infinite wire. Because if we have a nearly infinite wire, well, x squared begins to dwarf y squared, right? If x is much, much larger than y, then x plus y is basically x. And when that happens, x cancels out with x, you have y canceling out with one of the y's. So for a nearly infinite wire, our results for electric field, erase, I don't know, this. For a nearly infinite wire, our electric field simplifies to K times lambda over distance to the wire y. What will they mess up? Oh, since we're integrating not from 0 to L over 2, but minus L over 2 to L over 2, we do have a factor of 2 that comes out front. So you get 2 lambda times K over y, over our distance from a wire. This is the electric field from a nearly infinite wire. This is what we're gonna be working with for a little bit. This is the first charge distribution we're working with. Now, we're gonna look at other charge distributions, and other charge distributions use different integration techniques, but there are simpler ways to do this. This is the hard way. This is the hard way to get to our electric field. There are much simpler ways and much better techniques to figure out electric fields from charge distributions, and those techniques are encompassed in what we call Gauss's law. Now, I'm showing you the hard way, just so that later on when we talk about Gauss's law, you can appreciate the simplicity of that. For right now, we've went through the derivation. You've suffered me talking to you guys about this weird integral. You guys are free to use this result. Just remember that this result is for a nearly infinitely long wire. Meaning just large wiring, long wiring, large line of charge, large line of charge compared to the distance we are away from. Are there any questions, any thoughts, comments, concerns? Yes.
If the wire is infinite, would we use the previous one?
Yeah, if we're not infinite, then this is what needs to be used. I'm not going to really give you problems with non-infinite wires because we start to have issues with the fact that if we're not really infinitely long, then we're not going to have a perfectly vertical electric field. This right here was one of the assumptions we've made in assuming that this is long and well distributed. If we're right in the center of a charge, we're right in center of a non-infinite wire, this will work. But if we're even slightly off center, that begins to fail. But I'm not really going to give you problems with non-infinite wires. It's a little bit beyond the subject of this class. Is there any other questions? Again, the application of this isn't too bad. It is just this is what the electric is. And it's arguably a little bit simpler of an equation than from a point charge, right? It's not an R² thing, it's just a distance. But part of what you're going to be working on today is going to be on your classwork. Are there any questions before I get that to you? No, it's a little bit longer of a lecture. All right. So this is what your classwork is going to be today. If you have any questions, be sure to ask. Again, all of this stuff looks a little bit worse than it actually is in application, I promise. And if you haven't picked up your test yet, your tests are up here ready for you to pick up. You just gotta come by and grab them. I have A through L and then M through P. It should be. Yeah, it should be posted. If you don't see it for front, it literally is posted. Sorry, opposite. I lost. A through L and then N through so just so you're aware, your objects zero, local point here, and then look at this. Let's get hit this. The other ones. And if it's over.
But that take me down as well.
So question, please. What we're gonna do is. R. We have R. So we say, all right, it's 2000. So it's 2000. This is figure out what lambda is. Over here. Oh, figure out what lambda is. Not figure out what it is. Once they just have this. At this. Oh, no, okay, I did, so. Yeah, let's see. Sorry. We can figure out. This is the rock. We can figure out what that is. Plug in. Figure out what that is. Figure out what I send you. Now, with this. Just that. So if it's 2,000 minutes, it won't take us 10 cents. 1 into 5 centimeters long. That would be true for this. Times R. Constants. In any case, the deal. And this one is. That's why you gave me 50.
Well, you just plug in the E and then the R.
So it wouldn't matter we write necessarily, but on canvas, just that I don't get rid of the shape. Especially when it's